Some people say that it's very useful to be specialist on a part of mechanical engineering, like fraction mechanics or whatever. That means you can specialize at the university, and you can leave university as a specialist on something. My belief is that it's much more useful to have a general knowledge, general education. And later, if you are, for example, programmer, if you program the software for microcontroller or for washing machine, it's very useful to understand vibration phenomena in this mechanical subsystem, or to understand electrical drive.
In this episode, we go deep into the tram manufacturing business. More specifically, what does it take to be able to create a tram that does not crash into any infrastructure in the existing city? Have you ever wondered why there's only a couple of centimeters between the tram and the infrastructure? How do actually tram manufacturers in cities figure out which obstacles to avoid, what infrastructure needs to be built or avoided when a tram is put into a city? Robert explains from the beginning of where tram manufacturers in cities take decisions and what are the common tools they use, and how his company, which created a simulation engine called Tram, helps solve this problem.
The Inspiring Computing podcast is where computing meets the real world. This podcast aims to trigger your curiosity by talking to proficient and advanced users of MATLAB, Python, and Julia, who use these tools to deepen their understanding of the world, simulate, explore trade-offs, and gain insights that help companies add more value. In addition to this, we will also be talking to product marketing, toolbox authors, package developers, and library maintainers to see what drives the development and what issues they're solving for others to benefit from.
So Robert, welcome to Inspiring Computing.
Hello, Garrett. Thank you for having me.
So you and I met at a techno conference a few weeks ago. And when I got talking to you, your story actually inspired me, intrigued my curiosity, because a couple of months ago, I was visiting Amsterdam with my son, and we were catching a tram. And as we got on the tram, I was like, wow, there's only a couple of centimeters between the tram and the curve of where we were getting on. But before we get into too much about that, you were telling me a little bit about your company and what you do for a living. So can you tell us a little bit about your superhero origin story?
I'm a mechatronics engineer, basically. I work as an associate professor at the Faculty of Mechanical Engineering at the Brno University of Technology in Czech Republic. I'm also head of Department of Mechatronics, and I run Mechatronics Laboratory. I'm responsible for bachelor and master degree program in mechatronics. Maybe I also can say a few words about word mechatronics, because some of the listeners maybe are not familiar. As I understand, mechatronics is, or for me, mechatronics is a educational discipline which combines mechanical engineering, electrical engineering, software engineering, and algorithms. If you look around and you have any machine like washing machine, car, coffee machine, or even simple electrical drill, Parkside or whatever, you may see these four parts. So it has a mechanical body, there is electrical motor probably there, or some electrical actuator, or electrical heater. There is some electronics or electrical circuit inside. There is a tiny computer like Arduino or Raspberry Pi or something similar. And there is a software inside this. Part of the software can be called algorithm. It can be AI, but it also can be relatively simple control algorithm like PID or some signal processing algorithm, control image algorithm, or whatever. And this view of a machine, it's relatively new, because if you look at 50 years ago, passenger car, let's say, you don't see any electronics. You see some electrical circuits like ignition and lights and so on. But the schematics of whole electrical circuit can be on one page of paper. It's very simple, and otherwise it's pure mechanical. So to be able to understand the car, 50 years old car, it's quite enough to be a mechanical engineer. But it's not now. So what we want to do, we want today's students to understand today's machines, to understand, to modify, to develop, and so on. So that's mechatronics for me. And it also say a lot about what I teach, what we do, our approach, and so on. Maybe it's useful to say that that there can be different opinion of education, today's technical education. Some people say that it's very useful to be specialist on a part of mechanical engineering, like fraction mechanics or whatever. That means you can specialize at the university, and you can leave university as a specialist on something. My belief is that it's much useful to have a general knowledge, general education. And later, if you are, for example, programmer, if you program the software for microcontroller, for washing machine, it's very useful to understand vibration phenomena in this mechanical subsystem, or to understand electrical drive.
But what did you actually study at university?
I'm a mechanical guy. I studied mechanical high school, 4 years in mechanical engineering, and this is really my root of my profession. So I knew how to do drawings and how to construct machines and so on. Later, I studied at the university. We had a 5 years study. It was a long time ago, of course. I had last 2 years specialized on mechatronics. Mostly I'm mechanical guy by education. Yeah.
So, Robert, when you and I met, you actually were telling me a little bit about your company and the software you make. But I'm curious, so what exactly is this Tram motion, and how did you actually come up with this idea of simulating trams and figuring out the impact that the different layouts of trams have for calculating the envelope? Tell me more about this.
Tram motion, it's our software. Tram motion is a tool for simulating tram movement. Tram consists of several modules which are connected by joints. If you look at the tram, there are some bogies or undercarriages, different type. And if you look from the aerial perspective of the tram, it moves somehow. And the main question is, does it collide with infrastructure, everything around the track, buildings, platforms, and so on, obstacles? It may seem to be artificial problem because probably you haven't seen anytime the collision of the tram and platform. But I can tell you that it's really a really important and frequent problem. And who is the customer, or who is asking this question? Two sides. There are two sides. Tram manufacturer. The question of tram manufacturer is how to construct, how to design my tram to be able to go through the given infrastructure, given city. Every different and so on. The different side is a city transportation operator, let's say. They have inverse question. How to design, how to adjust, how to modify my infrastructure, my platform, and so on, that my trams or future trams will pass without collision through this infrastructure. Again, to simplify the answer, what is the tram motion? If I say simply, it's a software, it simulates kinematics, movement of the tram, calculates, we call it envelope. So the envelope of the movement, and determines whether it collides with given infrastructure or not.
You have to excuse my ignorance, as this is not the world I live and breathe in, but it sounds like it would be very reasonable for people to be simulating this all the time. How do people solve this without your software?
I try to explain it. How we come to this question or to this problem from the manufacturer side. From the very beginning, project is a cooperation between our company and my brother. My brother is also engineer. His education is aircraft engineer, which is interesting, but he worked for Škoda Transportation, which is a Czech tram manufacturer. And now he's with Stadler, which is a Swiss tram manufacturer. The situation is that every today's tram is designed according to the specific city, because specific city have specific infrastructure. So it's not designed from the scratch, of course, but it's about modification of a model which each manufacturer has. So what you do, you can, for example, the position of the bogie or position of the door or shape the front of the cabin. And if you think about it, moving this undercarriage, this bogie position slightly, it changes the kinematics of the tram. So you can influence, you can change, or if you change the length of the module, you can slightly modify these dimensions, and you can change the envelope of the tram movement. So basically it's optimization task. You have several parameters, like dozens of parameters, which you can modify, and you change the envelope of the movement.
So I'm curious of how did you actually come to this realization that this is a problem? How did that actually happen?
Yeah, it was at the end of December, and I was somewhere in mountains, in some mountain huts, and I had a call with my brother, and he described me this problem. The problem is I need to calculate this envelope of the tram, and if I ask my engineering department, they said, it's okay, we will do it for you. They use CAD tools. Normal CAD tools, like you have, if you design mechanical things, so the same tools, general CAD tool. We can do it for you, no problem, but it takes, and 6 weeks was the whole time for the whole task. 5-6 weeks, you had to submit the application for a specific city somewhere in Germany. I don't know. I was sitting in that hut and I drank like 3-4 beers and I prepared a demo in MATLAB, of course. It was nice evening. I remember it still. And this demo consists of some using of optimization toolbox. You know it very well. And as a result, there was animation using a MATLAB figure, animation of this little tram moving through some infrastructure. And that was the start of the whole project. My brother was quite impressed. I sent it to him via WhatsApp or this video, this animation, and he was quite impressed. This is how it starts. After that, we prepared more major demo using MATLAB script and so on.
Let me see if I get this straight, Robert. So you created a MATLAB script to do the maths of multiple trams or carriages connected together, and you're doing the kinematics of where the tram goes through and what the outermost point is. So on an ideal track, you've got 2 or 3 trams, they're moving along, and you can mathematically guarantee the most outer part of where the tram goes, meaning that for an infrastructure, you now know that the infrastructures have to abide by that measurement. Is that what you're saying?
If I'm talking a little bit deeper with how tram motion works, you have to define track, which is the railway in the track infrastructure, and then you have a vehicle, because the tram consisting of several modules. And you can have different type of modules based on the bogie, the undercarriage. It can be fixed, it can be rotational, and so on. And these two elements, the track and the tram, you define it in Excel file, which is quite useful because everyone has Excel. It's quite easy to edit the parameters and so on. There is a very simple visualization. So if you enter the parameter, you see the undercarriage moves that way. And then you open the Tram, you load this Excel file, these definition files, and you calculate basically kinematics. Yeah, we are using MATLAB inside, but in this MATLAB engine, you calculate the kinematics. You calculate distances of many points, and you visualize the result. And also you store the results back to different Excel files. After that, every user can read these Excel files with all the results, and he can, for example, plot it his own way or use it another way to post-process it as necessary. The basic task of the software is calculate the envelope of the movement. And if we are going even deeper into the detail, then we have to say that we have ideal track axis. So it's ideal axis of the track, and the bogie, the undercarriage, moves along this ideal axis. But beside this, if you look at the railway, there is a clearance, a little bit like in centimeters maybe. So the bogie can move left and right a little bit on the track. You have to somehow incorporate this clearance. And this is different in near platform, and this is different near 3 parts of the track and so on. Again, if you think about it and you imagine that this undercarriage has 4 wheels, then you have clearance in your track. Then you have 5 different positions, like central position, that ideal position. Then you have the whole bogie is on the right side, left side, and turning left, turning right. So complete 5 different positions of this bogie. And based on this, you have much more variants. Inside the software, we have 2 modes. Let's say we have the ideal mode, the axial mode. This is the ideal. And then we call it worst case mode. We consider all possible variants of all bogies on the tram, and we calculate the worst envelope, which can be much wider than the ideal one. And it is question now what the engineer will do, the user will do with this information, because this worst case variant of the kinematics can happen only exceptionally. So you have to employ your own domain knowledge to evaluate if this configuration is dangerous or not.
So let me see if I get this straight, Robert. So you have a couple of carriages connected to each other, but because the tram tracks are also got a little bit of clearance, a little bit to the left, a little bit to the right, that actually sources forces on the carriages before and after. And those forces also change in turn the position of the tram. So when you say the maximum or the worst case envelope, you're actually taking into account the propagation of the forces as the tram in its worst case scenario can have, right? So that is actually quite a complicated mathematical calculation.
Yeah. Well, the number of combination is really high. And that's why we use MATLAB, because in MATLAB, it's quite effective. The algorithm is quite effective, and we can calculate, and I'm talking about several hundred meters of the track. So we move our tram, let's say 300 meters from, as you said, from one platform to another platform, let's say, and we can calculate it in tenths of seconds. Comparing to days or even weeks, using standard CAD tools, it's really huge effectivity, increase of effectivity. Our tool, for example, with our tool, you can even answer the question. There are common situations in meeting. There are 20 people in the meeting, engineers, sales, and whatever, and they ask, "We have a problem with this passing through infrastructure. What to do with it?" And one engineer can say, "Well, what about to short this dimension of the tram?" And now you can do it in real time, let's say online. In online meeting, you can modify the dimension, click one button, and in few seconds you have result. So it's very increasing of effectivity in the tram manufacturer.
So effectively with the fast calculations, what you're actually doing is increasing the design exploration space. So then you can have many more trade-offs. What if then else scenarios by saying, what happens if I use this tram or that tram, these dimensions, if it's turnable or if it's rotational or fixed trams. And you can see the combinations by very quickly calculating the worst case scenario. But more than just being able to simulate it, you actually can see the animation, right? So you can actually see the trams moving from stop A to stop B, and you can actually see which point of the tram actually caused the worst case scenario. And you can see that as an animation. I'm guessing that makes a big difference in management meetings and making sure that everybody's on the same page when it comes to what infrastructure is needed or if anything needs to be changed.
You mentioned animation. This animation, we have one of the outputs of our tool is an animation of the movement of the tram. And it's interesting because using this standard CAD tools approach, you cannot have such an animation or very complicated. Then don't do it. Then they don't do it. They just explore the most critical parts of the track. And now we have complete animation of the movement of the tram. And it's interesting because some people, even in engineering in those companies, have seen it for the first time, the movement of the tram. If you look carefully, tomorrow we'll go to the city and you look at the tram, you can look carefully at the tail of the tram, for example, how it moves, and you will understand why it's shaped somehow. And it's not for only design art purposes. There are technical purposes because this tail moves somehow and it should not collide with infrastructure. And for sales, for example, it's very important to see this animation of the tram because they can show to their possible customers we have this problem under control, because the city operators has the same fear of this problem because as the tram manufacturer.
So as you're telling me about this, it feels like there's actually two use cases here. So I'm thinking there's the case where a city doesn't have any trams whatsoever. So this tool becomes very useful from designing specifications of the tram but actually more importantly, the city infrastructure. But then there's probably the other use case that I can think of is if a city already has a tram infrastructure, but they want to expand it, and probably they want to reuse then trams as much as possible. So they've already purchased trams. They want to make sure that the new track layouts actually work with the existing trams. Is that correct? Or are there other use cases?
Of course, as I said, there are two sides in this business: tram manufacturer and city operator. And the city operators or engineering bureaus, engineering offices working for them needs these calculations too. They don't need to know how to modify or how to develop new tracks, new lines.
Using MATLAB for calculations or these large calculations with all the different combinations, did you explore looking into maybe leveraging game engines? Because the visualizations seem to be very powerful and very realistic.
One can solve this problem using a gaming engine, yeah. But I'm not sure about the precision and about the control you have over the calculation, because our algorithm it's a numerical algorithm. So it's not symbolic mathematics, it's numerical mathematics inside. So we have a discretization of the track. For example, I think now we have 5 centimeters. So this 100 meters is discretized by 5 centimeters, and each 5 centimeters is calculated. The required precision of the calculation is really in centimeters or below centimeters, because the requirements for producing new trams, for example, the distance between platform and entering edge of the tram is very high. There is allowed to have few centimeters only, the distance. If you look to old tram, like 50 years old tram, there was maybe 20 centimeters stair. You have to climb up to the old fashioned tram. Now every tram is a low platform, so you don't need to climb anymore. But the required distance between the edge of the tram and the platform in few centimeters. The manufacturer even have to play with special hydraulic devices which lower a little bit the tram and allow to decrease the distance. Because the wheel of the tram itself can veer operation. It can change the diameter, at least in millimeters. 10 millimeter is the wear of the wheel. So you have to incorporate even this.
Diving a little bit deeper into the tech stack that you used, I think you mentioned earlier that you used MATLAB. Can you maybe tell me a little bit more why you actually ended up choosing MATLAB?
Yes. So first of all, I have been using MATLAB for 27 years or something like this. And I'm teaching MATLAB and Simulink for 20 years, modeling in MATLAB and Simulink, and I teach the basic programming first year students for about 5 years. Maybe I love MATLAB. It's a great tool for teaching, I believe. It's a great tool for engineers, especially again, my roots are mechanical. I'm at the Faculty of Mechanical Engineering, and typically students and staff at the Faculty of Mechanical Engineering are not programmers. They are not on software too much. So they mostly use script to analyze problems and so on. And for that purpose, it's perfect. It doesn't require compilation. So you have your results, your debugging is quite fast and so on compared to, for example, C. But once you want to develop an independent piece of software which has user interface and so on, then it's more complicated as a former MathWorks guy. And if you are talking about UI, because this is part of your question, we have been using for many years old MATLAB user interface based on Java. Just one example. If you have simple edit field, text edit field, that component, that widget in Java Swing has about 20 callbacks. Callback is a function which starts if something happens. If you click to the widget, or if you move your mouse over the widget, or 20 callbacks. And what MathWorks did, they took just only 1 or 2 callbacks to protect poor user to be overloaded with all these functionality. We are not poor users. We would like to be advanced users, and that's why we were not happy with this. And there was a way how to overcome this and go into the Java Swing properties and how to use Java directly to modify these widgets. And this is history. And what is the present situation? Present situation is that the standard way how to create application UI with user interface is to use App Designer, call it App Designer. We have App Designer, and App Designer consists of web technologies inside. But MathWorks did the same approach, or for me, it's the same mistake, that they enclosed everything and hid everything in some inaccessible box, let's say, and delivered something to the user which has for me, it is relatively low performance and it's limited. And one of the limitations, which is very important for us in context of Tram motion software, is a limitation in figures, in charts. For example, what we need definitely is callback. If you click on data points, we need to know which point was clicked. Because in our software, in Tram motion, if you click to the point of envelope plotted, then that module, that part of the tram, which created this problem, created this envelope point, will move directly to the position, so you can see exactly what is the configuration of the tram. And you cannot do this without callback to this level when you click on the point. This was one of the reasons why we started to explore our own technology.
You said something really interesting. In your program, when you click on the envelope, it goes to the exact point in time, the exact position, the exact tram that created the envelope. So you can actually fault find in the sense of say what caused this envelope and have a discussion around that regional element, right? Okay, so that's a fundamental feature. But now you're saying that with the MathWorks, when you use the app designer, it feels like it's a little bit harder to get to a place to reproduce that callbacks, because just like with the guide and now the app designer, MathWorks has hidden away and simplified it for people who've never created an app or a user interface in their life. But there is a turning point where if you want to do something a little bit more professional, it feels like you need some of these other things. So Java Swing put all of these 20 callbacks, as you mentioned, not by chance, but because there's a need.
Yeah. One of the motivation, one of the reason why we started to explore our own way, to say it in short words, we finished with the same approach as MathWorks. We are using web technologies, particularly we are using Electron.js of Chromium,
Mm-hmm.
the same engine which is in a Chrome browser or Edge browser. So there's Chromium for front end, and there is Node.js for back end. And you can communicate, and everything is encapsulated in one, let's say, software component. And if you are talking about the front end of this Electron.js for charting, we use Plotly library, which is quite well known for Python users. But because Electron.js is JavaScript-based tool, so we use JavaScript version of Plotly. And for the widgets, for the buttons and selectors and other stuff, we use Vuetify, which is again a tool which combines Vue as a framework for designing web pages with material design from Google. So the view of our software, of our promotion software, the appearance is based on material design, and the charting is based on Plotly. And as an output of this Electron.js, you can get exe file, or you can get exe file for Mac or Linux, or this exe file for Windows. And what is very important, and I'm now talking back to MathWorks, if you double click to this exe file, this Electron.js exe file, it starts really instantly. So it starts in fraction of a second. You see your own window, and there is a wait bar, let's say something like this. And what we do after starting the Electron.js exe file, we start as a sub process. We start the MATLAB. So it's basically a whole MATLAB compiled into the or MATLAB code compiled into the exe file, and between these two processes.
So you made the decision to go for the Electron to get the cross compilation, cross OS compatibility.
Mm-hmm.
You then use the Vue framework for visualization blocks and the web framework with a nice CSS design, fully customizable. And then you use for the charting, use Plotly, the JavaScript version of that. And then you have on the back end a whole bunch of communication between these infrastructures. But the maths itself is actually done by MATLAB, but it's not that your customers need to buy MATLAB. What you do is you deploy MATLAB, and then that is inside your program that you can ship on the different operating systems, right? And that's what you're calling the MATLAB engine.
Yeah. You to be able to use this MATLAB engine, this MATLAB exe file, you need only to install MATLAB runtime, which is for free for the user.
Yeah.
So from our side, we compile it in MATLAB compiler. It creates this exe file, but to run this exe file, you need to have MATLAB runtime, which is for free.
So a few things here jump out. You mentioned that the app designer and guide is useful for quick prototyping if you've never created a program in your life. I think the use case fits that nicely. That being said, it feels on the web front design, technologies have evolved at a much faster pace, and there are other ways of doing it. So that's why you combine the maths from the MATLAB, and then the visualization from Plotly, from the Python ecosystem, and then the whole Electron framework view from the web framework. So you have a nice program that you can share customers, and you use material CSS from Google to make it look nice, right?
Yeah. Again, I think the MATLAB is very good because basically our software is kinematics, that the important algorithms are about kinematics, about calculating positions of millions of points and distances between these points and selecting which point are a set of points which is the closest of some other line or whatever. And to develop this, you need something which calculates very fast with numerical objects like matrices. And it is very useful also to have a good visualization of the result of the kinematics.
Yeah.
So during the development, we used normal MATLAB figures. We did, as a prototyping, we didn't use app designer.
Okay.
We don't need it. Because for prototyping, you are fine with script. You run the script, and for example, you plot using normal MATLAB figure, you plot the tram and this position that you can look at it and say, this looks fine, the distance is here and here, and you have a result. So this is the development part. And the development of the UI, your final product, is something completely different.
Yeah. So it feels like you're touching on three large steps or groups or profiles, if you will. It feels like there's the brother who comes as a concrete problem. So there's the business/domain that you need to know that this is a problem in the first place, that, I never realized that cities or tram manufacturers had this challenge. So there's a domain issue. Then there's another part of what you're saying is for developing the maths and the algorithms. You liked using MATLAB. You created that first prototype. You got a very quick idea. You got the ball rolling, and that was very nice. But that is really, do you know the maths? And okay, so you're a university professor and you're teaching mechatronics. It's a tool that you're already teaching, and it allows people to have a better understanding of what maths in the real world works. But then when you come to the last component, you're saying there's another level, is the whole software architecture of how do you share something with someone else, which you now have to learn a whole bunch of new technologies and combine them. So it feels like in order to make this, you need these three big chunks, which is not so easy to master as an individual, but also not really taught as such, right? I mean, university, you're either the domain person, you're the software person, or you're the business person.
Yeah, I fully agree with you. These three components or three domains, it's quite difficult to combine it because, as also from your experience, the definition of the problem, the description of the problem or specification of the problem is like 50% of the solution. But to explain, software engineer to explain this problems, kinematics of the tram, I don't say it's impossible, but I think it's very hard. So it's our strong side that we can combine, from my position, from my point of view, how I see the world. And we are back in mechatronics approach to education. If you have wider knowledge of software, mechanical engineering, and maybe kinematics in this case, you can at least talk about it with people, and you can specialize. This project is also a learning project for me. I learned a lot. Before this project, I didn't use versioning system. Now we use SVN versioning system. I didn't use object as much because for pure mechanical or mechatronics modeling analysis, you don't need objects as much. But if you do a project with such a complexity like is Tram motion without OOP, without object-oriented programming, you cannot do it. It's. I don't say it's possible, but it will be very hard. So I learned a lot in this past years about, as you said, architecture, about objects, about development processes.
Yeah. So I have to ask the difficult questions. If you were to start again from scratch, now that you've learned a lot, would you have taken different decisions along the way? Or would you have still said, if you want a mathematical based user interface, the right combination is effectively using MATLAB's core computation engine, plus the Electron, plus the CSS and the web technologies, that's the right way? Or would you say, actually, maybe there's another way? I'm curious.
That's a difficult question, but I don't think that I would change anything. As I said, I love MATLAB. So if you love something, your possibility to maneuver or to change something is limited if you love somewhat. So I definitely, for development and for, as we call it, engine, but for core algorithm, I would use MATLAB again.
Yeah.
For visualization, I still don't see any other option. Maybe someone, because I didn't talk about it too much, but we tried also Qt, for example, for visualization. We tried something in Python for visualization, but I think that I don't say that Electron.js is only option to encapsulate Chromium with Node.js. There are other options, but I believe that Electron.js is the most mature thing, and some path will be shorter and something will be easier. Because if I do it again from the scratch, I can avoid some dead ends, but basically I would do the same.
Yeah. So I think creating user interfaces and deploying it to other people is actually a difficult process because there are lots of variables, right? So there's different operating systems, there's different frameworks, different dependencies, tool chains, and it's actually not easy to get your head around all the options. And then I think many people just take the path of least resistance, which is what they currently know. And that's somewhat random of where you've brought up in your area of influence. So when there's a will, there's a way, and smart people can find a way, maybe in the less optimal, but it ends up working nevertheless.
Oh.
But I do like it, find it inspirational on the mathematical side of things. What got this going? You articulated how MATLAB and still use that as a development part. That is nice. And I think you're right with people with a mechanical background. The path to get going and get some insights is actually relatively easy compared to other languages.
Yeah.
So I think also the Python ecosystem, it takes a while to get your head around it. And then I've got 10,000 options. You're actually creating more dead ends than you need to, which is the right visualization library. So math work is really easy. There's only one plot, one figure. You either like it or you don't. We move away.
Yeah.
The Python ecosystem is I'm going to choose all the other ones, which has its advantages and disadvantages. But nevertheless, it seems like this still beats hands down your CAD and maybe even Excel, because if they're not using CAD and if they're not using your tool, how do people do this? How is this actually done? Historically, is this?
Yeah. That's a good question. The Tram is not only software project or not only custom-made software. It's only product. The other softwares we did in the past was mostly for single company for single purpose. We didn't sell it to more companies. But if you enter to the engineering office, I think all over the world, you can see basically two different things. You can see very complex analysis like final element analysis or CFD or whatever. And then you can see quite simple calculations, which are typically done in Excel. Why Excel? Because everyone has Excel in his computer and anyone knows it and so on. And it has a lot of advantages, but it also has some disadvantages. And I think some of them are serious. And first is that Excel has some limitations. You can either program it indirectly in Excel cells, or you can use Visual Basic. I don't like Visual Basic. It's my roots. I was talking about my roots, but it's also important to say that I started programming in ZX Spectrum Sinclair. Again, Visual Basic is something similar to Basic in this spectrum. I really loved the ZX Spectrum, but it has its limits, and Visual Basic also has it. So this is point number one, limitation of Excel. Point number two, which is maybe the most serious for a company point of view, is intellectual property. Because if you directly write your equations into the cells, but also if you write it in Visual Basic and you lock it somehow, you can find on internet in few minutes the software for unlocking the code. So if you write something into Excel, either in cells or in Visual Basic, you are losing it. And I have seen many times employees leaving the company with flash disks with a lot of Excel files. It's quite serious. And if you have, for example, as a company, results of measurement stored in this Excel file to be used for calculation and so on, it's serious. And the third reason why not to use Excel or why to develop your own custom software is control of workflow. Every user can easily change the code, the content of the Excel file. Then you finally have several versions. Each engineer has his own version of the Excel file of the calculation. It's chaos and you don't want it.
Yeah.
For company management, you have little control over the workflow, over the calculations. So I think it's also important.
It's funny that Excel's so predominant given these three very well articulated things. But I think it's also the software computer science folk. They figured this out years ago, but there's plenty of people who never went through that background, right? So it's a bit of that idea of just because a group of people have figured out a problem, if they don't speak to the other group of people, then that other group of people can live happily ever after without ever knowing. So being able to cross those bridges is actually
Yeah.
an important element.
Yeah, that's true. That's true. I have seen many times in companies that they probably there has been some, at least here in Czechia, there was a wave of Fortran programming in 70s or 80s, and they still use some little small programs in DOSBox or however you run it, which are written in Fortran. According to my experience, today's mechanical or even electrical engineer is not a friend of software, friend of programming. Like I'm from the Faculty of Mechanical Engineering, and I know that that our mechanical engineers, typical mechanical engineers, don't like programming, and they are not even able to write simple software. Then they don't want it. That it's not about abilities or if they are capable to do it, but it's about dislike, I would say.
Yeah, the interest itself, right? So
Yeah.
I can imagine also like a mechanical engineer, they loved taking apart a car. So they would go to a garage and they'll disassemble the engine and then they'd like to put it back together. And that's what drove them. And that was like super cool understanding it and getting their hands dirty. And that's an element that kind of comes with a mechanical engineer. But I agree with you that in today's world, disassembling a car and fully understanding it, you need the electronics, you need the software, and at a certain moment, you can't put it back together again. It's not as easy as such. If people want to reach out to you and collaborate and learn more about this, what is the right way that people should reach out to you?
Just write me email or a LinkedIn message.
That's it for today's episode. I hope you enjoyed the conversation and found it valuable. If you did, please consider sharing this episode with your friends and family or anyone who might benefit from it. Also, I'd love to hear your thoughts, so take a moment to leave a review and let me know what you think. And if you haven't already, don't forget to give us a rating. It really helps us reach more people and bring you even more amazing content. Thanks for tuning in, and I'll catch you on the next episode.